Greetings, everyone. This particular video is going to focus on the notes for this Friday class, where we're going to talk a little bit more about how exactly we can start to break down um, questions involving forces, and specifically kind of talking about the idea of what happens when we have balanced forces and kind of how we can use that to our advantage. All right. So the first half is going to be kind of a guided note. So I'm going to kind of go through, talk you through what's going on. And the second half, I'm going to kind of focus more as I'm going to have you pause the video and kind of work through that second page of notes. It's kind of like your own practice. And then, I would like you to start the video again periodically so you can kind of see if you agree or disagree with the answers. All right. So we start with an FBD. And you notice that FBD on the left side of your notes has two forces acting on it. All right. Now, in this case, it has a tension pulling up and a gravitational force pulling down. Now, we talked a little bit in our lab last class about the idea of the difference between balanced and unbalanced forces. Now, balanced forces pretty much are exactly what you expect them to be. They're a situation where it looks like all the forces seem to kind of almost cancel themselves out, which seems to not cause a change in motion. All right, and we saw that a little bit in our lab, and hopefully our next lab, we're going to see in a little bit more detail how exactly that kind of works together. But for now, we're only worried about this particular case. So these two forces are balanced. Now, when forces are balanced, it means that we can actually use that to our advantage. All right, we can use it to kind of figure out maybe how much force each one is exerting. Now, looking at this question, we start with kind of something to tell us. So it says the object has a mass of 55 kilograms. All right. Now, at the end of the day, in physics, we always want to try and figure out as much information as possible. And this question is no different. So our goal is we want to figure out how much force is in the force of tension and how much force of gravity is acting on this object. Now, to do that, the very first thing we want to do is we want to kind of write down what we call our balancing conditions. All right. And this is just basically a statement that has to be true no matter what's going on here. In this case, our balancing conditions, or equilibrium conditions, as we might start calling them, is going to say that because these forces are balanced, the force that's going up has to be the same thing as the force that's going down. All right, and we're going to see that's going to be kind of a case throughout physics when we talk about balancing conditions. You're going to have your vertical forces equal to each other and your horizontal forces equal to each other. All right, now, in this case, our up force is our tension force and our down force is our gravitational force. So we go through and we replace that. So instead of saying up force equals down force, we're going to simplify it and we're going to say tension force equals a gravitational force. And again, all we're doing is just acknowledging that these forces are balanced, which means that the up and the down forces have to be equal to each other. All right. Now, we got our conditions. Let's try and figure out if we can solve for these things. All right. Now, we always try and look for what we know we can solve for first. We try to see what information we have that might be useful. And the only thing it tells us in this question is that the object has a mass of 55 kilograms. All right. Well, if we know the mass of an object, we know that we have a formula to calculate its weight, or Fg, which is exactly what we're going to do here. So the first thing we do is we're going to calculate Fg. Now, we've already reviewed this a couple times. We've gone through some practice. We just remind ourselves once again to calculate the weight of an object, the force of gravity. It's just the mass of the object times the gravity field of wherever that object is. Remember, we're going to be pretty much always assuming we're on the Earth. So it's going to be the mass times the gravity field. The mass is 55 kilograms. The gravity field on Earth is 9.8. Remember, if you said 10, you just want to round up. That's totally fine. On the AP exam, that's exactly what they will do. But if you want to be accurate to Earth itself, you want to use 9.8. So 55 kilograms times 9.8 newtons per kilogram. Right away, that gets you that the weight of this object is 539 newtons. And again, we're just using simple stuff that we know, using the formula we've come up with in a previous lab, using the information that we know, the information we've memorized. And remember, when you calculate the weight of an object, once again, you must turn the mass into kilograms. All right, and we'll do a little practice with that a little bit lower down here. Now, I know Fg, that's one of the two. But I want to also figure out how much tension is in the rope as well. Now, this is where our balancing conditions come into effect, because we know from above, we said these things are balanced. These forces are equal to each other, which means the tension has to equal the weight of the object. Well, if we know these two things are equal to each other and we already know what the weight is, then we know the tension is also going to be the same thing at 539 newtons, because these two forces are balanced. So, bringing that all together, we get that the tension in the rope is 539 newtons, and the weight on of the object is 539 newtons. All right, and again, the reason we bring this up is that it does seem kind of like, well, it's just two forces. Why did this isn't particularly interesting? We once again just want to get used to this idea that when objects are experiencing balanced forces, you're going to see kind of this combination where all the vertical forces have to equal each other, the up and the down forces must be equal, and all the horizontal forces have to be equal to each other. And again, we're going to practice that kind of through these notes as well. Now, the second piece of this, I've changed our diagram up slightly. So now, you'll notice, I have a box that's being held up by two ropes, all right? And it's just hanging at rest. The first thing we want to do is, of course, we want to draw an FBD. So, looking at this diagram and looking kind of in this box, we know the first thing that's acting on the box is there's gravity. So we know there's Fg pulling down. We also note that there are two strings that seem to be pulling up to support the box. All right, so I'm actually going to have two tensions going up. Now, if these ropes are identical and kind of they're both hanging straight up and down, we can think about this as each rope is basically supporting some of the weight of the box. And specifically, we can pretty much think about it as they're probably each holding up half the weight of the box. All right, they're kind of going to share the weight here. Right? So that leads nicely into the next piece, which is that we want to write our equilibrium conditions or our balancing conditions. All right? And basically, remember, that just means I want us to write an equation where all the up forces are going to equal all the down forces. Now, when forces are going the same way, all right, they actually work together and act like one bigger force. All right, it would be the equivalent of if I have an object being pushed by one gigantic rocket or an object being pushed by a lot of very small rockets. They're all the little small rockets are still going to add up to act like a much bigger rocket when all said and done. All right, so these forces are no different. What that means is that when I write my equilibrium conditions, I start by looking at all the up forces. In this case, it's just two force of tensions. So I'm going to say they add together. So I'll say the first force of tension plus the second force of tension. Those are all the up forces. All of those together are going to equal whatever the down force is. In this case, according to our FBD, there's only Fg. So our equilibrium conditions would look like Ft plus Ft equals Fg. And you can actually simplify this because these are actually the same value. You can just rewrite it as 2 times the force of tension equals the force of gravity, which basically is exactly what we set up here. This is telling us that basically the force of tension in each rope is going to be half the weight. All right. Now, just like we did before, we want to figure out what Ft and Ft are equal to, so we look to see what is given to us in the problem. Again, nothing about Ft is told to us, but we are told the mass of the box, which means we can calculate the weight. So we're going to find the weight of the box. Now, this is where I told you earlier, we're going to have to convert things into kilograms sometimes, and this is one of those situations. So, in order to go from grams to kilograms, you have to divide by 1,000. All right, and that will get you into kilograms. So in this case, the mass of the box is actually 0.256 kilograms times the gravity field of the Earth, which once you can remember, in reality is 9.8, or if you want to simplify, use 10. And you'll get that the weight of the box is 2.51 newtons. And again, we're just practicing using this formula, Fg equals m times g. Now, we know Fg, which means now we can use it to our balancing conditions to figure out the tension as well. So we know that 2 times the force of tension equals the weight of the box, which means the force of tension is just equal to the weight of the box cut in half. So go through 2.51 newtons divided by 2. The force of tension in each rope is going to be about 1.255 newtons. All right. And again, it's something where it's exactly what we expect it to. If you have basically two identical ropes and they're both pulling up, well, it would probably make sense that they're going to share the weight equally because there's really nothing to kind of differentiate between the two of them. So they're going to do the exact same thing. All right. And again, we're just getting used to this idea we can have balancing conditions. And in this case, we're getting used to the idea that we're starting to see what happens if we have multiple forces going in the same direction. All right. Now, this is the first half of the notes. This is kind of the guided part. So, hopefully you were following along. The second piece is one that I would like you to kind of work through it yourself. All right. And periodically, I'm going to kind of review and talk about the different ones. So if you could, let's just talk through this question before I let you pause this video and work on it a little bit. So you'll notice I have a lovely little drawing where I made a fan cart. All right. Now the fan is on and it is trying to push the car to the right. Unfortunately, there is a string that is tied to the cart and then tied to a bumper on the track that is not allowing it to move. So it is at rest. All right. So what we're going to end up doing is we're going to figure out, when all is said and done, the amount of force that is acting on each direction of the cart. So we're going to draw some FBDs and we're going to figure out how much force is acting on it. All right. So what I would like you to do, please, is I'd like you to kind of go through and answer the next couple questions. See how far you can get. If you get stuck, feel free to unpause the video. But if you could, take as much time as you need. Once you're ready, unpause the video, and I'll kind of walk through how to do some of these questions. All right? Fantastic. So I hope you had a chance to kind of work through these particular questions. This is kind of our first real step into kind of having to think a little bit about some of the forces acting on an object and kind of using our idea of what balancing conditions and using the clues in the problem to figure out what's happening, right? Now, the most important piece here is the idea that it says this cart is not moving. Even though it's trying to, it's not actually moving, right? Now, what that means is that if it's not moving, it's moving at a constant velocity, right? Which technically it's a constant velocity of 0, which I know can be confusing. But even if it's at rest, we still say it's experiencing constant velocity, all right? That's the first thing. Now, we saw from our lab that if an object is experiencing constant velocity, that means the forces have to be balanced, all right? And that's going to be a fundamental rule of physics, and we're going to talk about it in more detail in the next lab as well. We're going to kind of come up with a law that governs that. But if it's constant velocity, it must be experiencing balanced forces, all right? Next, I ask you to draw a force web for the cart. Remember, the force web is basically us taking all the different objects that could be exerting a force on the cart and then kind of mapping it out. This one's a little complex. I actually have about 5 circles when all's said and done. So, of course, you start by drawing the circle for the object you care about, to the cart. Then you start drawing circles for all the other stuff. So, I'd have the cart, I'd have the fan, earth, string, and track. All these are different things that could be exerting a force on the cart itself. All right? And kind of going through, remember, earth, you draw a line from earth to everything because it's always pulling on everything. Right? In this case, the cart and the string are going to be experiencing a force because there's going to be a pull between them. The fan and the cart are going to be experiencing a force because there's probably going to be a push between them. And the track and the cart are going to be experiencing a force because the track is going to be keeping the cart from falling to the center of the earth. All right? Now, if you have more or less on this, that is totally fine. The force web is just kind of a general way for us to organize our thoughts. And in fact, as we get more comfortable using FBDs, we're going to start to move away from the force web just because occasionally it can get a little complicated, or in this case, a little cluttered. All right. So at this point, that's kind of the first 3. Again, if you haven't had a chance to, try and go through and do the next 3 as well, because these are the 3 that I think are very important. They're definitely based off of what we talked about earlier. So if you haven't had a chance, pause the video and do the next 3 ones. Okay. And if you haven't had a chance to work through all of this, then we'll keep going. So the next question is, draw an FBD for the cart or fan. So basically, we're going to treat the cart and the fan as one object here. And we draw the FBD. All right. So we want to think about what forces could be acting on this the cart fan. All right. Well, the first one we can think about is that gravity is going to be pulling down on this thing. So there's going to be an FG going down. And it's not falling to the track, so there has to be a normal force going up. Now, we also know that the fan is pushing it forward, just like we saw in our lab, which means it needs to have an applied force going to the right. And we also know that there is a string that is keeping this thing from moving. So if this is trying to push it to the right, the string is more than likely pulling it to the left to kind of counteract that push force. So when all is said and done, we should have an FBD that looks something like this. And again, you get that nice plus pattern, which is showing right away. It's pretty easy to see. This is showing balanced forces. All right. And one of the things we're going to start getting used to is that we're going to start getting comfortable with the idea that we can start drawing our vectors. Remember, those are that's what we call those little arrows. We can start drawing them the correct length to actually show, if someone looked at it, which forces are bigger than the other forces. All right. Now, the next couple ones are both calculation questions. So again, I want to know how much force each one of those things is equal to. So we start with the stuff that we know. All right. In this case, usually it's easiest to start with weight. Again, it tells us the weight of the fan cart itself is about 850 grams. And of course, that's not exactly what we want, so we got to turn into kilograms. So again, You take that, divide it by 1,000, then multiply it by the gravity field of the Earth. When you go through and do all of that, you get that the weight of the fan cart is 8.33 newtons. So that's how much it weighs, right? And that gives us the keys that we need to finish the rest of this question. So it says, so the last piece, determine the values of the other forces on your FBD. Now, in a little parentheses, I say you might want to see which forces are balanced with each other. That's kind of coded language for me saying you need to write out your equilibrium conditions. And in fact, as you start going through the different forces questions I'm going to give you, you must write out your equilibrium conditions if you want to get full credit. And I will be looking for them because that is an excellent and quick way for me to know if you recognize which forces should equal which forces. Right? So in this case, our FBD actually now has forces going in the vertical direction and the horizontal direction, but they still follow the same rules. All right? If we're experiencing balanced forces, that means the up forces have to equal the down forces, and the right forces have to equal the left forces. Okay? But I do want to make this very clear. You cannot match an up and a left, a down or a right, or kind of mix the horizontal and vertical forces. Okay? It has to be vertical and horizontal. So in this case, if I'm going to write out my conditions, well, vertically speaking, up equals down. So the normal force acting from the track is going to equal the weight of the cart. So Fn equals Fg. Well, guess what? We already know what the weight is. We just found it. So if Fn equals Fg, that means the normal force of the track on the fan cart is also 8.33 newtons. All right? And again, we're just using our balancing conditions to figure that out. Horizontally, we can do the same thing. So in this case, we know the horizontal forces have to be balanced as well because this is experiencing constant velocity, which means that the right force equals the left force, What that means is that Fa, the applied force, is going to equal the force of tension from the string. Now, it might be a little frustrating first because we're like, well, I don't really know if it told me either of those two things. But if we go back and look at the top of the problem, it tells us at the very end that the fan is pushing with a force of 9 newtons, which right there gives us all the information we need. Because that tells me that the applied force that the fan is providing is going to equal 9 newtons. So Fa equals 9 newtons. And if the applied force is 9 newtons, then according to our balancing conditions, the tension force has to be the same. So the tension force from the string is also 9 newtons. All right? So hopefully a chance to kind of work through that and practice using kind of our ideas of equilibrium conditions, the idea of what it looks like when we have balanced forces. This is going to be a big part of physics going forward, looking at different situations and kind of determining how forces are balanced or unbalanced and how that might affect the situation or affect the object. All right? So with that being said, if you have any questions, of course, please feel free to come by during office hours. Feel free to shoot me an email. But other than that, that's all I got for you today. Have a great rest of the day.